So let's start with what we intended to do today. We'll want to discuss the three-body problem. Um, what are the bodies? Is one gravitating mass, another gravitating mass, and also a smaller mass, which is probably a satellite or asteroids or any celestial objects. Okay. So what's the difference between what we've learned before? So what we've learned before is we've discussed all about two-body problem. Our assumption is we have one big mass and one small mass. This small mass could be a satellite or an asteroid, and then this is usually Earth, and sometimes in some cases this will be the Sun or Mars. Okay, so how does the trajectory of this small mass around the bigger mass looks like? So we can get all that from this two-body equation. Remember, we have derived the constants of motion, angular momentum conservation, and also mechanical energy conservation, orbital equation, all derived from this. This simple equation can give us so much stuff here. Okay, so now what's a three-body problem? It's something like this. Okay, so you have three body all with masses. Okay, so in this case, how would the trajectory of this will look like, or the trajectory of this and this, how would they look like? Okay, and let's see how they look like if, let's say, they are about the same mass. So look at this. If you can see this animation, so it's really unpredictable. Yeah, if you look at the motion of all three masses, this is a three-body problem where all these objects are gravitating towards each other. So their trajectory is what we call chaotic, very chaos. Very chaotic, because we cannot predict the trajectory, because what we are doing so far for two-body problem is we want to look at the trajectory, we want to predict the trajectory, how long it's going to arrive there, what are the speeds, where are the positions. But in this case, three-body problem, it's because, as you can see, it's haywire. You can't figure out where it's going to go afterwards, and it's very, very sensitive to initial conditions. That means if you change the initial conditions by a little bit, the trajectory is going to be completely different trajectory. Okay, so a few mathematicians or engineers back in the 1700s, 1600s, well, they figured, okay, this problem is too complicated for us. Let's make some assumption. Let's make some make it easy a little bit so that we can actually study it. Because as right now, there's no way we can analyze the problem of three-body. So let's simplify a few things. So let's just consider that M1 and M2 are the gravitating mass. That means their mass, both of these masses, they're going to influence each other. But the third mass, it's so small compared to these two. So the third mass is not going to influence the motion of the other two masses. This is the same assumption we did in two-body problem. Satellite is so small compared to the mass of Earth, so we that's how we get the gravitational parameter and everything. Okay, so and then let's make another assumption that mass 2 here is orbiting around mass 1 in a circular orbit. Let's simplify the situation. Let's not look into the weird trajectories. Let's make it simple. Assume it's a circular orbit. You want to see what happens. Okay, and then this is what I told you just now. The third mass is considered really very, very small compared to mass 1 and mass 2. Okay, so what kind of system like this that exists in real world? I mean, what kind of real world application? Well, you can imagine it like a Sun-Earth satellite. This is Sun, Earth, satellite. Or another three-body system like Earth, Moon, and satellite. That is also a three-body system. Or Sun, Jupiter, asteroid. That is also a three-body system. We look at into two massive bodies and one bodies with negligible mass compared to those two. Okay, so we call this usually CR3BP, circular restricted three-body problem. So if you look it up on the internet, there's a lot of studies doing this one, but we are not going to go into too much of the mathematical detail and everything. We're just going to look at what happened. So today, I'm going to show you the interesting things when we simplify the three-body problem into the circular restricted three-body problem. Let's see what happened. Now, if you assume that your Sun, Earth system, the three-body system, there are 5 points which I would like to call this a parking spots. Okay, let me explain this. Okay, so these 5 points are called Lagrange points. Okay, he's French, so probably I would say Lagrange, something like that. I don't know. I think those who learn French can correct me on that one, but I will call it Lagrange. So if we assume circular restricted three-body problem, we find that there are 5 Lagrangian points here that is special. So what is so special about this? What's so special is this: if you are stuck, if you're placed in these points here, one of these points, L1, L2, L3, 4, and 5, you will tend to stay there. That means it's if you are at this point, for example, you will follow the Sun and Earth system. Okay, like this. For example, I will show you this GIF right here. So it's like that. So if you can see these GIFs here, it shows the 5 Lagrangian points, the green ones. It is actually fixed to the rotating Sun-Earth system. So if you are, for example, if you're a rock in space, okay, and if you're stuck if you somehow get yourself into this Lagrange 4, L4 point, you'll stay there. Okay? You will stay there. So you will move along with, you will dance along around the Sun just like that. Okay? Mind you that this is not exactly on the circular orbit of the Earth. It might be a little bit different. But that's the magic of three-body problem here. You find these 5 parking spots, I would say. If you are in the vicinity of this point, you will tend to stay there. Okay? So this is pretty amazing. So let's look at these Lagrangian points one by one, and then what they do basically. Okay? So the first one is the point between the Earth and the Sun, L1. Okay? Now that point there receives, well, they get the same attraction from Earth and from the Sun. So that is why if you stay there, you kind of balance yourself between the gravity pull of the Sun and gravity pull of the Earth. So that's like a balance point, if you can imagine that. Okay, but the mathematics is more complicated than that. I think that statement is, in general, can be accepted. So if you receive the same gravity pull from both sides, that's the point, L1. So it's actually situated 1.5 million kilometers away from us. Very far. Just to give you an example, Moon is about 200, 300 kilometers, 1,000 kilometers. So, but L1 is an unstable point. That means if you're stuck in there, it's easy for you to be kicked out by some perturbation. Okay? It's unstable in that case, so if you can stay in there, but it's easy for you to get kicked out as well if there's a little perturbation pushing you away. But it has a very useful space application, and actually we have launched a satellite there already stationed in L1 point to study the Sun. So it's easy to study the Sun from here because you will never get the Earth in your way. You can always see the Sun, and also you are close enough to Earth to send back any data from the spacecraft. So that's a perfect point for spacecraft to study Earth. Okay, and let's look at L2. L2 is a point behind Earth. Now, at this point here, if you can imagine, yeah, that point, because it's away from the sun and it's farther from the sun as compared to Earth, the period's supposed to be slower, right? Period is supposed to be smaller and it should move slower. But because of the gravity, combined gravity of the sun and the Earth, it kind of tuck the spacecraft in. So you can imagine it like a spacecraft where it's being pulled by both gravity of the sun and gravity of the Earth. So that point is also another parking spot. You can put your spacecraft there. But again, it is unstable. If you put anything in there, if you get a little perturbation, you might get pushed out from that parking spot. Okay. The James Webb Space Telescope. So they are planning to, NASA is planning to launch a spacecraft, put it in L2 point to act like a space telescope. So you can observe the deep space from that point. Okay. And you are also close to the Earth to send back any data or anything like that. So let me just stop over here if you want to look at the animation. Okay. So let's attend to any question if you have one. Oops, what's happened? What is this? Okay. All right. So hopefully everyone is still here. Oh, there's a question. Okay. Oops. That's the point. So is the moon included in these points? That's a good point. That's a good question. The moon is not in either of these Lagrange points. The moon is actually orbiting very close. If this is to scale, the moon is orbiting very close to Earth. Because imagine the distance of L1 is about 1.5 million kilometers, and the orbit of the moon, I think, is about 300,000 kilometers. So it's closer. You could have that means these points are actually a lot farther than the moon. But I would say also this is the Sun-Earth system, the Lagrangian points of the Sun-Earth system. You can also have a Earth-Moon, Earth here, Moon here, and then we have our own Lagrangian points for the Earth-Moon system. Okay, and Jupiter also, if you treat it as a three-body system with the Sun, you can have Sun, Jupiter, and then they also have their Lagrangian points. And I will get into that because we are going to see really weird orbits around the in our solar systems that you couldn't think of. I mean, well, how do these orbits appear like this? It doesn't make any sense from two-body problem point of view. Okay, so what's the trapezoid inside? The trapezoid, there's nothing trapezoid inside. This is actually just to show a distance. L4 and L5 is actually about equidistance from Earth and from Sun. Okay, it's about the same distance. So at these 2 points here, L4 and L5, they receive the about the same gravity pull from both Earth and the Sun. So that's why these L4 and L5 are also a parking spot, I would say. So if you're stuck there, you're gonna be stuck there for a long time. Same effects. Effects like how? You can imagine it like I said. You can imagine it like a parking spot. So if you are a rock in space, if you're wandering around and then you get sucked into one of these points, you will stay there. Okay. Just because L1, L2, and L3 are not stable. That means if you get stuck there, but if you get a little bit push, you can just get out of there. But if you're stuck in L4 and L5, you're going to be stuck at there a long time, because these are stable points. You imagine lah, just imagine if you put a marble, a ball, a small ball, on a plate, and if you put a ball in a bowl. Okay, so if you put a ball on a plate, it's easy for you to actually get the ball out of the plate. You can just take skate, give it a little flick, and then it will go out of the plate. So it's unstable. If you put the same ball in a big bowl, for example, well, it's harder for the ball to get out of the bowl. See, if you give it a little flick, you might have to give it a really strong flick to get it out of the bowl. So imagine L4 and L5 is like a bowl, and imagine L1, L2, L3 is like a flat plate. Okay, this a function. Well, if you're talking about right now, we are not talking about a function yet. It doesn't have, I wouldn't say it's function. It's let's say it's an interesting things that happen when you consider three-body problem. You find these 5 points can act as a stable point for applications to happen, spacecraft or whatever. But what I'm going to show you, I'm just going to give an overview of what spacecraft application we can use for this, but I'm going to show you also what's naturally happen in space. Okay, so that's I explained Lagrange point 1, point 2, and Lagrange point 4 and 5. Okay, so 4 and 5 here, these are stable points, meaning bodies that stay there tend to stay there. Okay, in our system we probably have probably a small rocks, asteroids, whatever, living there. Okay, dust and asteroids tend to accumulate in these regions. A body that orbits the sun in the vicinity of these points are called a Trojan. So whatever, if let's say we have an asteroid living in that point, we call that a Trojan. Most popular ones are Jupiter Trojans. Well, if you have sun here, Jupiter, and then the Lagrangian points of the Jupiter Sun system, we call that the Trojans asteroid. I will show to that later. But just want to let you know that if you park your spacecraft here, then you don't need much maneuver. You can save your fuel. It doesn't, it's not easily kicked out from these 2 points. Okay, as opposed to L1, L2, or L3. So you can use that as a relay information, or you want to put your spacecraft far away, for example, and study the sun or other planets. You can do that. So we have seen applications for L1, L2, that spot, and those 2 spots as well, L4 and L5. What about L3? So L3, neat. What about L3? So we have yet to found any application suitable for us, useful for us in L3. That's it's there. It's still a Lagrangian point, but I don't think there's an application. Why do you want to put a spacecraft there in L3? It's way too far from Earth. It's always hiding behind the sun. The Earth cannot see any spacecraft there. But I think I remember I read science fiction about this. There's it's about building an anti-Earth, your evil space station there. So if you put your evil space station there, no one from Earth can ever see you. So yeah, if you're an evil genius, billions of dollars, you can build yourself an anti-Earth there. Space station, put it in L3, no one is going to see you. Okay, so these are the 5 Lagrangian points which are co-orbiting with Earth, or I'm talking about the Sun and Earth. Yeah, I mean this blue planet can be anything, can be Jupiter, can be Saturn. They all have their own Lagrange points. Okay, but I'm showing you here is a generic Sun planet Lagrangian points. Could be anything. Okay, now let's go back to Trojans. Now look at this figure here. Those dots are actually asteroids. I think we are all familiar with the white dots. those are the asteroids in the asteroid belt. Right, we learned this in high school, or probably you've read some encyclopedias, and you know of the asteroids living in the asteroid belt. So that's not a problem, we know that. But look at these green ones. This one, Trojans and Greeks. If you notice, these green asteroids, where do they stay? They stay in the L4 and L5 of the Jupiter Sun system. Let me get back to you here. Remember, let's say this is Jupiter, the blue one Jupiter, this is the Sun, and L4 and L5 are here. You see, there are a lot of Trojans, a lot of asteroids accumulate at these two stable points, L5 and L4. Okay? So not all asteroids are in the asteroid belt, but they also stay here. Okay? So Jupiter have about 7,000 of Trojan asteroids. We, Earth, Sun, three-body system, we only have one or two, I think. We don't have that many, probably because it's not that stable. But Jupiter Sun system, they have 7,000 Trojan asteroids. Okay. Yeah, I mean asteroids. There are big and small asteroids. You know. You remember the last time we watched the video? There's a lot of sizes as well. Okay. So this is actually what is happening in real world, natural system. If the blue one is Jupiter, does the planets such as Earth and Mars are not affected by the Jupiter system? No, they are too far away. You mean the dynamics of Mars and Earth are not affected by the Jupiter? You see, is that if we think of it like this, when we talk about two-body problem, we only talk about one planet and one satellite, right? So that's two-body problem. When we talk about three-body problem, like I said, we look at only two gravitating mass. So in this case, when we want to look at this phenomena of Trojan asteroid, we look at Sun Jupiter system. Okay, so we kind of ignore everything else. It doesn't really affect the trajectory of these asteroids at all. Okay, so if you look at the Sun Jupiter three-body system, we can see that in its L4 and L5 there are these green asteroids called Trojans. Okay, Trojan asteroids, yes. Any asteroids that are living in the vicinity of L4 and L5 is called Trojan. Computer Trojan. No, this is Trojans. Yeah. So for Sun and Jupiter system, they have 7,000. I think for Sun and Mars, probably very little. For Sun Earth system, we only have one Trojan, I guess. So in our Sun Earth three-body system, I think we only have one asteroid living in one Trojan asteroid in our system, Sun Earth system. But Sun Jupiter system, its Lagrange points, they have a Trojan system. Yes, Lee, really, any name for it? Yeah, there are 7,000 something. I think scientists usually they give names to each of these asteroids. So like say for example, this group right here is called Trojans. These groups right here, they call it Greeks. Okay, and my lecturer last time, his name is Professor Hildas. He's got an asteroid named after him. So there's an asteroid up there which has a name of my lecturer. So if you contribute to science, significant enough, you get an asteroid named after you. So probably in the near future, you'll have an asteroid named after me. Asteroid Salah. Anyhow, um, because the Greeks found, oh no, Adini, usually all these celestial objects, traditionally, they will use the names from the Greek and myths or Rome myths, is it really? So they use this, so they will always use nama-nama dewa perang. Like Mars is supposed to be, I think dewa perang or something. And then Mercury is dewa something. I don't remember. Pluto I think is I don't remember. I need to read back my Greek mythology. Into like Oumuamua, remember Oumuamua? That's not Greek though. That's from the Pacific Islanders mythology. So it's probably some kind of a god they will for the Pacific Islanders. Yes, that's how they name the celestial objects. Okay, this is not interesting enough. Okay, Trojans. Okay, fine. In the Jupiter Sun system, in their L4 and L5, there are a lot of asteroids accumulating in that region called Trojans. Now let's look at the. If you can you see the can you see the orange dots? Okay, orange dots are called Hilda. Okay, Hilda is another weird, not weird asteroid. I say weird because its orbit is so weird. Okay, now for Hilda, I'll show you some video later on. Don't worry. If you can see these little red orange dots, those are called Hilda asteroids. Their aphelion, their apoapsis, is situated in L3. Okay, the apoapsis of these Hilda asteroids, I mean they have an orbit too. They have like if you consider two-body orbit, they actually have an elliptical orbit, and the apoapsis is in the L3 region of Jupiter. Okay, now there are a lot of Hilda asteroids. We call them Hildas. Okay, and it's so weird. They are all in elliptical orbit actually. Each Hilda asteroid is actually in an elliptical orbit. But for some reason, I'm not too sure. Well, for some reason, if you plot them all, it will look like they are accumulating in a triangle orbit. Can you see? It looks like a triangle. This is the L3, L4, L5, and L4. It's so weird. It looks like it's a stream of asteroid going through in a triangle shape like this. But actually each Hilda asteroid has an elliptical orbit. This is so interesting. The first time I saw this, hey, this is an asteroid with a triangular orbit, which is pretty cool, I would say. Hey, how do you come up with that? You know, there must be some interesting mathematics behind it. Okay, I have to study more on this one, like how do they actually get into this triangular orbit. But it's actually not a triangular orbit. Each Hilda asteroid is an elliptical orbit, but if you collect them all, they will look like this. Hilda asteroids. Okay, and let me show you here. Pictures are no fun. Can you see that? Okay, this, if you imagine the middle here is the Sun, and that's Jupiter, and then this green area here is L4 and L5, where L4 here, L5, where the Trojans live. Right? So that's how they're co-orbiting with Jupiter. And then the red asteroids, those are Hilda asteroids. So fascinating. I don't know if you are as excited as me, but Hilda asteroid is their orbits are amazing. Okay. So I hope you understand how L4 and L5, L1, L2, L3 move with the Jupiter Sun system. Yeah, it's not a fixed point in space, but it's co-moving with Jupiter. Okay, let's see another GIF here. So if I co-orbit with Jupiter, that means if I go around in a rotating frame, I'm rotating with Jupiter now, so Jupiter looks like is in a fixed place. This is how the asteroid looks like in a Jupiter Sun three-body system. So you can see L4 is here, yeah, L4, L4, L5, L5, and some weird orbit in L3. So this is how it looks like. So that's what Lagrange points is. It makes sense to look at it graphically in a rotating frame like this. When it's moving together, then you don't actually see it like the Lagrange points moving together. Well, how does this work? So if you can see it clearly like this, I will show you more interesting orbits later on. But let me attend to some questions if you have them. Is there an explanation about Hilda? Oh, 2D. Yeah, it's just if you combine all the Hilda asteroids together, it looks like they form like a triangular stream. It's not actually orbit. There's no orbit that is going. There's no asteroid that is going from here to here back to here. But the accumulation of all the Hilda asteroid will look like that. The red ones and green ones collide. Is there where some asteroid? Oh no, they don't know how to control themselves, so they don't collide. As you know, asteroids are really they have different sizes. Some are really small, some really big, and you must remember also that space is very big, and actually the distance from the Sun and Jupiter is also very far long. The moon. No, the moon of Jupiter is very close to Jupiter itself. Very close to Jupiter. I don't think they have the exact number of moon of Jupiter. Jupiter has so many moons. Oh, let me tell you this. Do you know that Jupiter is as important to life on Earth as the Sun, the Moon, and everything else? Why is Jupiter so far away? It's very useful for Earth. Okay, this is the reason. Now, Jupiter is a planet so big that it is a big planet. It has a very strong gravitational pull. So what it does is actually it's pulling all these asteroids, all these weird rocks in space into its orbits, so that the Earth is taken care of. So there will be no asteroids hitting Earth. There will be no weird space objects hitting Earth, because Jupiter is like a big brother of the solar system. It has a really strong gravity pull that it attracts one way or another all the asteroids in the solar system. If it doesn't attract the asteroids to be its moon, it will attract all these asteroids into its orbits, like in Trojans, Hilda asteroids. So you can imagine Jupiter as a big brother from far away, taking care of you, sucking out all these asteroids, not letting them hit the Earth. So that's why we have to love Jupiter as well. And actually, when scientists are looking into a star system which has a planet like us, when they're trying to find an Earth-like planet, they will always look for an Earth-like planet with a big planet nearby, like Jupiter. So if, let's say you found a star, and then you found that star is orbited by some bodies, and then you found that there's one body that is not too far to the star, not too close to the star, so the weather is just nice, the temperature is just nice. They will also look for another big planet to act like a Jupiter. Yeah, Jupiter Oni-chan. Okay, so let's continue. So we know about the Jupiter, the Trojans and Hildas now. Now let me show you a different thing. Now what we have seen is just now is just the point where asteroids accumulate. Now these asteroids, when they accumulate in L4 and L5, they perform a really weird orbit. Look at the left one. The orbit is like this. It's moving around L4, so it looks like a tadpole. I don't know how they call this a tadpole. Doesn't look like anything like tadpole to me. Okay, and you see here there's an if there's an asteroid here in L4, the orbit looks like that. You can't call them circular orbit, elliptic orbit, parabolic or hyperbolic. It's just, we call it tadpole orbit. So weird. Just to show you how it looks like, can you pick one green dots here and look how they move around? Okay, they move around pretty much like this. Okay, and there are also what we call a horseshoe orbit. This is even weirder. It wanders around from L4 back to L5 and then back to L4 again. So its orbit will look like this. It's going around the three-body system like that. It's so weird. Okay, but just to let you know, it looks like a horseshoe and tadpole when we look at it in a co-rotating form. Okay, let's look back into here. Can you see this? There's a green asteroid that is kind of lost its way here. Actually, it's not losing its way. It's in the horseshoe orbit. It wanders so far off the L4, but it's going to come back. So they all have weird orbits. You can't explain them using circular orbit, elliptical orbit, parabolic, hyperbolic. No, it's totally different thing. So we got no name for better name than tadpole and horseshoe, because it looks like a tadpole, looks like a horseshoe. Okay, so now this is mathematics. Yeah, I will show you how it look like. This is a tadpole orbit. Okay, don't look at the green, right hand one yet. Look at the left one. Now, the Earth has something in its L4. Sorry, L4, is it L4? Yeah, L4. L4 point. I don't know. I still don't know how to pronounce the name. Krishna. Let me see. How do I pronounce this? Cruithne. Oh, okay. I give up. Cruithne. Okay. Cruithne. Okay. Look at this Cruithne. So Cruithne is a space object. It's a rock, something big rock. That is, it kind of makes sense if you look at it from here. Yeah, yeah, that's an elliptical orbit. This is the Earth in a circular orbit. But if you imagine it as a three-body system, Earth, Sun, and around L4, you can see this Cruithne is having like a tadpole orbit around L4, horseshoe orbit around L4. Remember, we know that L4 is a very stable point, so if it stays there, it tends to stay there. Some people call Cruithne the second moon of the Earth, which is so weird. We only know of one moon, but some people call this object here is the second moon. All right. So if you look at it in the three-body system, Earth, Sun, it looks like it's orbiting the L4 point like a horseshoe orbit. All right. And then let's look at this. A Prometheus. A Prometheus is a moon of the Sun, but it's a moon that it is not really orbiting the Sun. It's not orbiting the Saturn in a two-body Keplerian orbit. Okay, Prometheus is the moon of Saturn that moves in a horseshoe orbit. Again, let's look at the left one first. So the white one is Prometheus, green one is Saturn. So this is actually the moon of Saturn. Yeah. Look at the left one first, and then because it's so affected by the Saturn's gravity, it moves a weird way. So you can see there's not too much difference. But if you look at the right hand one, then you can see why a Prometheus is in a horseshoe orbit. Look at it. Okay, it's here. It's moving there. And then it comes back. Into the other point and then comes back. So it will trace like a horseshoe shaped orbit here. Guys, three body system is really weird. You will find orbits that does not make much sense. There comes back again. There you go. So a Prometheus is a moon of a Saturn. A moon of Saturn, and it moves in a horseshoe orbit around Saturn. Okay. Alright. This is another example because Saturn is so big and it has so many moons. We have now this is a bit different. Now this is a three-body system involving Saturn and its moon, its bigger moon called Dione or Dione. I don't know, probably Dione. So this is three-body system: Saturn, its moon Dione, and two smaller masses. Now this small masses is actually Saturn's moon as well. One is called Polydeuces, and one is called Hellenes. Okay, I think that's where Helena comes from. Okay, and it moves in a weird orbit. This is in L5. This is in L4. If you can imagine the Lagrange points there, this is where Polydeuces lives, and this is where Hellenes live. Okay, and Dione is here, Saturn is here. So this is another three-body system: Saturn, Moon, and small bodies. It is fascinating. It's so weird, the orbit, and it comes back like which is spring. Okay, I'll attend any questions. Doctor, why the Cruithne stuck at same point instead of going through its orbit? Well, it's actually it's not stuck in same point. It is in its orbit. In a three-body system, you can see it's following a horseshoe orbit. Okay, so this is that's why when you look at things as a three-body system, Sun, Earth, and Cruithne, for example, you can see that there is orbit that it cannot be explained using two-body approximation. Okay, what it does is actually it's lingering around the L4 point. It's actually lingering around here. Okay, we call this liberating. Liberating means well, orbit is not really I think correct word. We call it liberating. It's going around this point here. So that's one cool thing about this Lagrange points. You can actually orbit the points. Okay, but the orbit won't look like anything that we've learned before. It looks so weird like this. So what kind of orbit, what kind of trajectory that can happen in L4 and L5? Well, these two orbits, tadpoles and horseshoe. Okay, so we see some examples. Cruithne is in L4 of Earth-Sun system, and it traces like a tadpole orbit here. Well, not really tadpole, a horseshoe. Okay, almost a horseshoe around L4. But if you look at it in the inertial frame, it will look like this. But if you look at it in the rotating frame, it will look like this. It's going through this trajectory. Now for Saturn and its moon system, the Sun and Saturn, you can see another weird moon here at Prometheus, which is actually its orbit is an horseshoe orbit going from L4 to L5, back to L4 again, just like this. Back here again. Okay, so you can only see the shape when you do the rotating frame. Okay, This one also a tadpole orbit in these two regions here is all moons that are orbiting these two Lagrange points, the ball that we were talking about. Okay, you can read about the Cruithne part. Actually, I wrote a paper on how to create a spacecraft which follows us like Cruithne. I call it quasi satellite. Yeah, that was interesting. So these are very interesting. Now, what we have looked into is are the natural happenings in our solar system. We usually only heard of moon going around a planet, like our moon going around our planet. So we can explain that using two-body problem, no worries. You can explain how Phobos and Deimos is orbiting around Mars as their moons. You can use two-body approximation, no worries. In fact, if you need to explain the motion of all the planets around the sun, you can always use the two-body approximation, the Keplernian. So that's okay. As far as for our applications are concerned, that is a good approximation. Now, when we want to go a bit deeper, we want to look at what will happen when you have two gravitating mass, and then what will happen. So they come out with the circular restricted three-body problem, and then look at the nature. You look at the nature. What will happen? Is our calculation on Lagrange points correct? Well, as they see, it happens in real world as well. You can see this Trojan horse liberating around L4 and L5. You can see Hildas asteroids where the aphelion is always in the L3. It's amazing. We've simplified the three-body problem, but we can still see what we can analyze from a restricted problem. Okay, and then we also look at there's possibly there will be some orbit that will follow this weird trajectory around L4, L5, like these two. Turns out in real world there is some weird asteroids that is orbiting the L points according to the horseshoe orbit, tadpole orbit. Cruithne is one example. Prometheus is one example. This one, Polydeuces and Helens is one point. So these are natural happenings. Now, because it happens in natural and looks fine, it looks stable, it stays there for a long time, why don't we send our spacecraft to one of these Lagrange points and do similar things? Why don't we send a spacecraft so that it can be our Polydeuces? Why don't we spacecraft around Earth so that it can orbit the Earth in the same way like Cruithne does, or Helines? Okay? Yes, there is one case. One of the cases is what we call a halo orbit. Okay? As you can see now, although Lagrange points is just a point in an empty space, its peculiar characteristic is that it can be orbited. Okay, imagine that this blue is Earth, and middle here is L2 points. We can actually send a spacecraft to that L2 point, and then that spacecraft will orbit that point like this. Send it here, do some kind of interplanetary trajectory, go around these L2 points and orbit it. Okay, top view it looks like that, side view looks like that. Weird, huh? So weird. Actually, we already sent a spacecraft there for solar observation and hemispheric. Okay, hemispheric observation, I think. Solar observatory and hemispheric observation. So we already have a spacecraft that is sent in L2 points and it's orbiting like that. We call this orbit halo orbit. But remember lah, it's so far away. It's like 1.5 million kilometers. Okay. Now, what else can we do with L2? We can also send a spacecraft so that it orbits L2 in what we call a Lissajous orbit. Lissajous. Again, I think this is a French name. I hope you forgive me if my pronunciation is not correct. Lissajous orbit. Okay, same thing. It orbits L2, but it's not really periodic. The orbits looks like this. Weird, but really interesting. Really interesting. You know, if you only learn about two-body problem, we cannot even imagine this kind of orbit. Look at that. It's like a batik in orbit. And there is a plan to send a spacecraft there. It's called Gaia. G-A-I-A. Okay. This is Earth. Send it to so that it orbits L2, and this is how it looks like trajectory around L2. Okay. This is Gaia spacecraft. Okay. Hopefully you can see this. This is the plan to send spacecraft into the Lissajous orbit around L2. Okay, look at that. That's the spacecraft. GAIA. This is a project mission from European Space Agency. So weird. Spacecraft orbiting something like that. Okay. Alright. Okay. So let me attend to any questions if you have one. Okay. So those are what I've shown you here is when you simplify a three-body problem into circular restricted three-body problem, you will find interesting things. That's what engineers do. When they have too complex of a problem, they simplify it. And then when they do this analysis, they found that there are 5 Lagrange points which are, they would say it's stable. You can actually park there. It turns out that L1, L2 and L3 are not stable, but it's still Lagrange points. Asteroids can accumulate in these points. And L4 and L5 are stable points. So that means if an asteroids or rocks or anything does accumulate here, it's hard for them to get out. And then we found also that these Lagrange points, you can actually orbit them. Okay? Orbit them how? Is it like a two-body problem orbit? Circular orbit, elliptical orbit, hyperbolic? No. We found so many examples. We found the tadpole orbit, okay, like Cruithne and Prometheus. Sorry, not Prometheus. The Polydices and Helines. Okay, they go around L4 and L5, and we see a really weird horseshoe orbit like Prometheus, where it orbits L4 and then goes to L5 and then goes back again. Okay, it can become possible because of the interactions of multiple massive bodies on Earth. If you need to look at the mathematics of Lagrange points, I encourage you to look at this paper right here. Okay, it involves Cruithne equations and everything. Okay, so that will be all for today. So this is probably your first time I'm doing engineering without any numbers or minimum numbers. But the point of this is to show you there are more orbits possible for your space mission. We are not only restricted to our assumptions of two-body problem, although two-body problem can become really useful, but there are some other weird dynamics, weird space mechanics that you need to look out for also.